Hello Antioch Bears, Mr. Crawford here, going over the Integrated Math 3 Practice 2 assignment. This is about exponentials, functions, and their graphs. Today in this assignment we're going to be looking at lots of different types of functions. We're going to be using tables to generate points. We're going to put the points on the graph and then take a look at the basic shape and whatever else we can get from that, alright? So, starting with the first one, we're going to discuss a linear function. A linear function always makes a straight line when you're graphing it. You know it when you look at the equation if the highest x, like this, is to the power of 1. If they don't write an exponent, we understand that to be 1. If this is the type of equation you're looking at with an x to the power of 1, know that you're going to get a straight line when you're done graphing it. Alright? We're going to do an easy one. This is just f of x equals x. Alright, this is the basic linear graph. I'm going to use -2, -1, 0, 1, and 2 for my x's. And if I were to take these numbers and plug them into the function, notice that there's nothing to do here. As soon as I take -2 and plug it in for x, it's just going to tell me, hey, f of x is -2. So my second coordinate is also -2. That's going to happen with every single one of these. -1, when I plug it in, going to give me back -1. 0 is going to give me back 0. 1 is going to give me back 1. 2 will give me back 2. So I'm going to plot each of these points over here on this graph. -2, -2 would be left 2, down 2. Sitting right here. -1, -1 would be left 1, down 1. 0, 0 is the origin. Right in the middle there. 1, 1 is right 1, up 1. And 2, 2 is right 2, up 2. Notice that all these points we're making do indeed make a straight line, as we said it would, because this is a linear function. Right? Quadratic functions, they make parabolas, this U shape when they're graphed. The equation will always have an x to the second power in it somewhere, right? There might be other stuff going on, that's fine. If you see an x to the second, know that when you graph it, it is going to make a parabola. It's known as a quadratic function. I'm going to use the same points I had a second ago, -2, -1, 0, 1, and 2. And notice that the function is just x squared. Every x I feed this function, it's got to square it, raise it to the second power, and then spit it back out to me. So -2 raised to the second power, if you can imagine that, right, is really just -2 times -2, which makes a positive 4. If I plug in -1, -1 to the second power is positive 1. 0 to the second power is 0. 1 to the second power is 1. 2 to the second power is 4. Notice that you got some repeats in the y column here. That always happens with quadratics. You get a lot of repeats. So I'm going to go to -2, 4, which is left 2, up 4. -1, 1 is left 1, up 1. 0, 0 is the origin. 1, 1 is right 1, up 1. And 2, 4 is right 2, up 4. And we have ourselves a parabola. Like so. Polynomial functions, third degree and fourth degree. We have this here and here. I'm going to use my same points. -2, -1, 0, 1, and 2. And this time I have to raise it to the third power. Which means, if you can imagine, if I'm taking -2 and I'm raising it to the power of 3, I'm making -2 multiply itself 3 times. -2 times -2 is 4. 4 times -2 is -8. If I take -1 and plug it in, -1 to the power of 3 is -1. If I take 0 and plug it in, 0 to the power of 3 is still 0. 1 to the power of 3 is 1. Positive 2 to the power of 3 is positive 8. When I go to graph these points, -2, -8 is left 2, down 8. That's a little off my graph, but that's okay. I'm going to estimate it down there somewhere. -1, -1 is left 1, down 1. 0, 0 is the origin. 1, 1 is to the right 1 and up 1. And 2, 8 is to the right 2 and up 8. Notice that this does not make a straight line. It does not make a parabola. It makes this little snake shape, like so. Fourth degrees are going to look a lot like second degrees or quadratics. Sometimes there can be some loops in here, but there won't be for this one. We got -2, -1, 0, 1, and 2. If you take -2 and raise it to the power of 4, you'd be writing out 4 -2s, multiplying them all, and you would end up with +16. -1 to the power of 4 is a +1. 0 to the power of 4 is 0. 1 to the power of 4, 1. 2 to the power of 4, +16. If I go to -2, 16, that's left 2 and up 16, way up here somewhere. -1, +1 is left 1, up 1. 0, 0 is the origin. 1, 1 is right 1, up 1. And 2, 16 is right 2 and up 16. So you get another one of those U shapes. And this is true for any polynomial of degrees higher than this. If it's an odd number degree, like this one was the third power, right? And even linear functions that are to the first power. Notice how one end is down and one end is up, right? One end is down, one end is up. That's true of all odd degree polynomials. If we did one that was the 5th degree, it would look a lot like this, or the 7th degree, or the 9th degree. Whereas even numbered powers, like the power of 2, produces ends that go the same direction. They could both be going up, or they could also both be going down, but they're going the same way, like this one. X to the 4th, both ends going the same way. Same was true for x to the 2nd. It would also be true for x to the 6th, x to the 8th, x to the 10th, so forth. All right. Backside. I actually screwed up on this. I meant to put this one as a radical function and this one as a rational function. Alright, radical functions, this is what a radical is. Some people refer to it as a square root sign. That's true. Technically you could also have cube roots, if you write a little 3 in there, or fourth roots. Those are all radical signs. Alright, we're doing the basic one, the square root of x. My x is -2, -1, 0, 1, and 2. And something strange happens the first time I go plug this into this function. When you take the square root of a number, you're being asked to identify which number times itself equals me. So I know, for example, that the square root of 25 is 5. Why? Because 5 times 5 equals 25. The square root of 100, for example, is 10. Why? Because 10 times 10 equals 100. Well, if you try to plug a negative number under a square root, especially on a calculator, it's going to tell you that there's an error, or that it's impossible, or it can't do it, because you can't ever take the square root of a negative number. So no negative numbers can be plugged into this. I can't generate any points out of that. If I plug in 0, that's okay, because the square root of 0 is 0. If I plug in 1, the square root of 1 is 1. If I plug in 2, the square root of 2 is a number, but it's an irrational number. It's a decimal. If you typed it in on your calculator, you're going to get 1.4 and a whole bunch of other stuff, right? So I'm going to change that to, since I can really pick anything I want for my x, to a 4, because I know for sure that the square root of 4 is equal to 2, because 2 times 2 is 4. So that gives me a nice even point to graph. I'm just going to graph these three. 0, 0 is the origin. 1, 1 is right 1, up 1. 4, 2 is to the right 4 and up 2. And you'll notice that the radical function has this kind of shape to it. I call it the wave. Right? The reason there's nothing over here on the left-hand side is because the left-hand side is where all the negative x's live, and you can't plug negative x's into this function. It won't work. You can't take the square root of a negative. So no points show up over here. It begins right here and goes out that way forever. Rational functions are a fraction. You'll notice that it's 1 over x in this situation. Whenever x is at the bottom of the fraction, you have a rational function. I'm going to use my same points, -2, -1, 0, 1, and 2. If I take -2 and plug it in, I end up with the fraction 1 over -2. Well, that's really just -1/2. I could also call it -0.5 if I wanted the decimal version, but I'm cool with -1/2. If I plug in -1, 1 divided by -1 is -1. And if I plug in 0, I can't do that one. There's an old rule about mathematics you might have heard. You can't ever have 0 at the bottom of a fraction. It doesn't work. You cannot divide by 0. So 0, much like the -2 and -1 for this one, is not going to generate a point. There's nothing there when we go to graph in a minute. Positive 1, if I plug it in, 1 divided by 1 is 1. If I plug in a positive 2, 1 divided by 2 is 1/2. 1/2. So when I go to plot this, -2, -1/2 is left 2 and down 1/2. -1, -1 is left 1, down 1. 0 doesn't have a point. There will be nothing through here. 1, 1 is to the right 1, up 1. 2, 1/2 is to the right 2 and up 1/2. And what ends up happening is you generate these double curves with a rational function that look like this. Alright? Cool. So now let's get to some more complicated ones, which were part of your homework. I gave you 6 functions to graph, starting with y equals 3x minus 2. Let me generate a couple of points here. We got xy. Let me try -2, 0, and 2. I'm just going to do 3 this time. If I take -2 and plug it in right here, this would be 3 times -2, which is -6, and -6 minus 2 is -8. If I plugged in 0, 3 times 0 is 0, minus 2 is -2. If I plug in 2, 3 times 2 is 6, 6 minus 2 is 4. -2, -8 would be left 2 and down 8. Again, it's a little off my graph, so I'll put it about right there. 0, -2 would be down 2. And 2, 4 would be right 2 and up 4. I think you can see that this is a linear function, making a straight line, as straight as I can draw it freehand. And we should have known that because we saw x to the first power, so we knew it had to make a straight line. This one, because it has x to the second, I know is going to end up making a parabola, right? The U shape. I'm going to use my same points, -2, 0, and 2. If I plug in -2, -2 to the second power is 4. -2 times -2 is another positive 4, then the minus 3. 4 plus 4 is 8. 8 minus 3 is 5. If I use 0 and plug it in, it basically cancels out this first part because 0 squared is 0 and -2 times 0 is 0, so I just get -3. If I plug in positive 2, 2 squared is 4. -2 times 2 is -4, and minus 3. So 4 minus 4 makes 0, and 0 minus 3 is -3. So I got a -2, 5, which is left 2 and up 5. I have 0, -3, and 2, -3. So I think I got a parabola that looks something like this. Again, if I wasn't sure, if I wanted to generate some more points, you guys are totally welcome to do that. Plug in any value for x. Plug in 1, 3, 4, 5, 6, on and on and on. You'll find the corresponding points there. X to the third plus 4. It's a cubic function. This should make a snake shape when I'm done. Same 3 points. If I take -2 and raise it to the third power, I'll get -8, and -8 plus 4 is -4. If I plug in 0, 0 to the third power is 0, and 0 plus 4 is 4. If I plug in 2, 2 to the third power is 8, and 8 plus 4 is 12. So I'd have points of -2, -4, which would be left 2, down 4, 0, 4, which is up 4, and then 2, 12. I'd go to the right 2, and I'd go way up to 12, somewhere up in there, and I can see the snake shape, right? Something like that. Down here, we have 1/2 x to the fourth minus 3. Because this is an x to the fourth, it's probably another parabola looking thing, right? I'm going to start with -2, 0, and 2. See if that gives me a good enough picture. If I take -2 and plug it in for x to the fourth, -2 to the fourth is 16. If I multiply by 1/2, I get 8. And 8 minus 3 makes 5. If I plug in 0, this turns out to be 0. I get -3, because 0 minus 3 is -3. If I plug in 2, 2 to the fourth is 16. 1/2 times 16 is 8, and 8 minus 3 is again 5. So I've got negative 2, 5, left 2, and up 5.